Let's discuss starting of a DC motor. In fact, almost all motors have starting issues. During startup, many motors draw overcurrents, inrush currents. Let's discuss it first. For example, assume that we are having a DC shunt motor. Here is armature circuitry, and let's say here is field circuit connected shunt or parallel. Here is the applied source voltage, terminal voltage, and here you see a DC motor connection diagram. And then you can draw equivalent circuit of armature circuitry. Here is array inside this guy and an back EMF in armature circuit. That is the terminal voltage applied. So here is a Kirchhoff voltage law around this loop. Applied terminal voltage can be written as current of armature times array plus induced EMF across armature. Ladies and gentlemen, armature EMF is equal to Ka times flux time angular speed. So during startup process, when machine is standstill position, omega is 0. When omega is 0, induced electromotive force is 0. When this guy is 0, current will have starting value. So armature current startup value or starting value is equal to terminal voltage over array. Startup current is equal to armature current when angular speed is 0. We call startup current starting current of armature. As you see, armature current startup value is equal to terminal voltage over array. First of all, there is a problem. Array is generally a small resistance, just like a few ohms, let's say 5 ohms for example. So let's say terminal voltage is 200 volts. In such a case, the startup current would be 40 amps. It is generally 10 or more times higher than its rated armature current. It is very large current. Startup current is approximately 10 times larger than rated current. So it's a problem. Problem for voltage source, problem for armature conductors as well. There's a problem because you have produced DC armature by using some conductors. Here you see on the screen. But during startup process, you force conductors at 10 times higher current, overcurrent. So there's a problem. It causes some fatigue in conductors. There would be some damage in conductors. So our job is limiting startup current. One of our job is this. The other job is maintaining speed gain. For example, machine is at standstill. There is no angular speed yet or RPM speed yet. And then you speed up machine up to its rated value, for example. Our aim is gaining speed in machine without causing overcurrents. So we should limit startup current by using some techniques. Ladies and gentlemen, here's the startup current equation. For example, if you want to limit startup current, you can decrease terminal voltage. Or you can increase array. Beep beep. Ladies and gentlemen, you have already manufactured or designed the machine. You cannot change array. Perhaps you can add some extra rheostat here. I mean starter, R starter. Some startup resistances or rheostats will be included here in armature circuit. It is adjustable to limit current. So in the equation, the included Rx will be here. So Rx will be here. Instead of this operation, you can increase this guy, external element, to limit startup current. Or you decrease terminal voltage to decrease startup current. Those are the approaches to limit startup current. Okay, how can you manage in reality? We generally use startup rheostats because it is very cheap. By using simple resistances, of course, high-grade powerful rheostats we use to limit armature current. Of course, we can use adjustable voltage sources, but it is a bit expensive, so generally we prefer a simple method and cheaper method, which is using starting rheostat. We use this guy. It is something like this. Not a smooth change. Here are some steps. For example, here we have 1, 2, 3, 4 resistances, and in 5 steps we start machine. Here's a handle. Handle is on the off position initially, and then we choose 1. We are starting the machine, and then 2, 3, 4, 5. Here you see 5-step starter. When you reach the final step, that means you have about to run in steady state, the handle will be locked by using such an electromagnet. Here's an electromagnet. When the handle comes 5th or last stage, the handle will be pulled by electromagnet, will be locked here, and then the continuous operation will start till you switch it off or till there is a failure in power system. For example, assume that there's a failure in supply voltage. It goes down to 0 due to a failure, a problem. The electromagnet here leaves the handle, and here's a spring mechanism. This handle moved back to its original initial position, which is off. It is resetted, as you see. Here's an electromechanical locking mechanism. Here you see a starter having 2 electromagnets, I will mention. But first, that is the off position, and then we step by step move to final position. Let's say 1, 2, 3, 4, 5, 6 step. When you reach 6th step, here's a C-type electromagnet. This handle will be locked by this electromagnet. So starting mechanism let the motor move continuously, operate continuously. You can leave your hand here because here's a spring mechanism behind the handle. Otherwise, if there is no electromagnet here, this handle moves back to its original position. Let me show you. Here's, for example, another type of starter. It moves back to its original position when there's no locking mechanism here. Here you see 6-step starter. There are different designs, different quality resistors. For example, here in this example you see 3-point starter. Here in this example you see 4-point starter. It is different due to patents, especially. What is the function of starter? First, limit startup current, armature value, limited by using extra resistances here, stepped resistors. The other is maintaining continuous operation by locking, and safety when there is a power failure here. The electromagnet leaves the handle and lets it to its original off position by means of spring mechanism here behind the starter. Behind the starter here, you cannot see here. The mechanism and operation is not important here, but let me emphasize what is important. Here in this circuit there are different approaches. Some control or check armature current, whether it is there some current. Some checks field current. In fact, that is must. Remember, our major aim is to gaining speed from standstill to the rated speed, for example. To manage this, remember Newton's equation. That is the Newton's equation by neglecting viscous friction here. That is angular acceleration, alpha. To gain speed, alpha must be positive. To manage this, torque motor shaft torque must be larger than load torque. If you neglect friction, mechanical torque is equal to induced torque inside the machine must be larger than load torque. Torque A, remember, was Ka times flux times armature current. So you need mechanical torque, ladies and gentlemen, and it must be larger than load torque. You need some magnetic flux to manage this. You need some current and magnetic flux. In shunt or serial machine, magnetic flux comes from field current. Field must be different than zero to have some torque induced, or field current must be different than zero. So there must be some field current. Let's take here in this circuitry. Here are some designs here, proper designs. I don't deal with the design, the complexity here. In case here is something cut, for example, assume that here is no field current. If here is no field current, there will be no electromagnet current, there will be no locking, or there is nothing to let handle move in clockwise direction. Perhaps here's a locking mechanism keeping the handle in its off position. First of all, there must be some field current different than zero to produce magnetic field. Otherwise, there will be no induced torque inside the machine. You cannot increase speed. So here is something to check field current. So the initial condition, field current must be different than zero. Field must be different than zero. Otherwise, torque cannot be produced. Torque must be larger than load torque to start up for positive acceleration. So the second condition, you should apply, let's say, check field, check field and field current, then apply starting method. One of the methods would be using external rheostat to include. The other method would be applying a variable voltage source. Reducing terminal voltage will let you to decrease or limit startup current. So by using such a method, you can limit startup armature current between desired region. Interval. That is the issue related with startup process. The detail is not important here. What important is the problem. There's a starting problem due to electromotive force here, because it is 0 when machine is at standstill. Due to that phenomenon, here would be larger startup current, overcurrents occur, so you should limit it. There will be some damage in winding or power supply, so you should limit the startup current by using some methods. Methods will include changing terminal voltage or adding some extra rheostats. But while doing that, initially at a zeroed condition, you should check field current. Otherwise, there will be no induced torque, there will be no movement, no rotation. That's all about starting process.